So this is comparing Bluetooth and Wi-Fi on the frequency band it uses. So what it does, you know that both Wi-Fi and Bluetooth uses 2.4 gigahertz. Wi-Fi uses other bands as well, but this is like the base band for it. And in that band, it's a range of frequencies, basically. It's divided up in channels. And here you see how the channels are divided for Wi-Fi versus Bluetooth. It's a little bit simplified, it's a little bit more complicated than this, but it's kind of there to illustrate it. And as you can see, the Wi-Fi channels are really wide. And if you have a wide channel, you can fit more information, which means when you transfer something on the radio there, you get a faster throughput. That's one part of the reason. The other part is that when you connect to Wi-Fi, you connect to a certain channel, and you have that channel during the entire connection. Okay? Bluetooth does not do that. It jumps, it does the frequency hopping that you probably heard about, which is another reason why Bluetooth is slightly slower, because it needs to do this dance along the different channels to do things. So those two reasons together is the reason why Bluetooth is slower than Wi-Fi. Bluetooth does frequency hopping because it wants to be robust. It's important to transfer the information that it gets there. Wi-Fi is more like we assume that everything is going to be fine, sort of principle. So this is basically, if you think about this, Wi-Fi is designed for one purpose: high throughput, reliable infrastructure. Bluetooth, ad hoc. We don't know what else is going on in the radio space there. So that also led to other protocols coming up, and this is what I'm going to talk about today. I'm going to talk about Wi-Fi and Bluetooth, but also a bunch of others that is good to know for app developers, so you have an understanding of why they are there and what their use is and when it's good to use them. Wi-Fi, well, let's start with that one. It's been going through a couple of generations. So it's in 1997, the first version came, wasn't very fast, 1 to 2 megabit. And then it just incrementally got better. It was like a pause in between 2013 and 2021 until Wi-Fi 6 came. Wi-Fi 7 came this year. I have a Wi-Fi 7 router. It's really fast. It's ridiculously fast when you have a Wi-Fi 7 capable device. And in a few years, we're going to have an even better one with Wi-Fi 8 with a 10 gigabit connection, basically. So it's like, it's going to be fast. The naming, the IEEE standards, I don't know how they decide those letters. I don't see a pattern really. They probably have some lookup table or something, I don't know. But there are some stuff in Wi-Fi that is good to know, especially if you're an app developer. Let's say you have a companion device that you want to hook up to your home network. How do you give it the Wi-Fi? Well, you all have done the thing like onboarding a smart plug or something like that, and you get the which Wi-Fi do you want it to join, and then you have to type in the password, right? Really bad UX and kind of awkward way of doing it, because the device knows the credentials for the Wi-Fi, so why can't we just say, please give it to the companion device? And there is a standard for that is supported for Android from Android 10 and onwards, called Easy Connect. That's a marketing name. The protocol is called Device Provisioning Protocol. It's supposed to work for iOS also. I haven't gone into the details there, but it should work. It's super simple to use. This is basically what you do. You create an activity for result contract, and you launch it with a settings.activity process Wi-Fi Easy Connect URI. And you pass it to URI. And this URI is something you get from the device. Usually, when you have a device that supports DPP or Easy Connect, it's printed as a QR code on the device. It can also be transferred in a way that you scan an NFC tag, or even you connect with Bluetooth just to retrieve it. The standard doesn't specify how you get this. What's a DPP URI? It looks like this. This is an example one I generated for a fake device. So basically, I call it my device. It has a serial number, and then it has a bunch of data in that string. And you can just generate a QR code. You scan the QR code with your app. You get the URI. You pass it into the code here. And you're done. What happens then is that the system takes over. And you get this dialog. And it says, oh, do you want to allow my device to connect to this Wi-Fi? You can choose a different Wi-Fi or whatever. The whole process is then handled by the operating system. So next time you sit in a project where you're gonna pass over Wi-Fi credentials to a companion device or smart home device or something, then you know how to do it. Of course, if you have to support anything below Android 10, you have to fall back to the old, ugly, enter your password thing. Okay, that was one thing. The other thing with Wi-Fi that people really are not aware of is something called full and low latency mode. It's basically you pin the Wi-Fi chip to go into a low latency mode. The effect is that you will have a slightly lower throughput, but each package will have higher priority and be processed faster. That means that you have lower ping, basically. So this might be useful when you want to have like a VoIP call that will be very reliable, or like real-time gaming, online gaming, etc., etc. Then you might want to utilize this, depending on your use case. Easy to use, you get the Wi-Fi manager, you say create a Wi-Fi lock, you pass in the tag for the Wi-Fi mode full low latency, give it a name, you say acquire, you do your stuff, and when you're done, you say release. There are some requirements here. The app has to be in the foreground, it has to be connected to an access point, etc., etc., etc. So you can't do it in the background. Okay. The next thing is multicasting. So we rarely do this, but if you need to do your own multicasting implementation on Android to listen for multicasting packages or send multicasting packages on the local network, then you need to use a multicasting lock. It's also pretty much the same principle. So you take the Wi-Fi manager, you say create multicast lock, give it a name, and then you acquire the lock, and then you can do your multicasting processing. The thing is, if you don't do this, you can't receive multicast packages. You can probably send, but you cannot receive any data on that is multicast by other devices, which means things like MDNS and stuff like that that broadcast on the local, or multicast on the local network, you won't see those devices. Why is it like that? Well, the Wi-Fi chip is optimized, so if it has to process every single package that comes in, it's gonna use more power. So this will use more power because it basically will open it up for other packages that is not directly addressed to that device. This is the reason for this. So basically, we lock it, it will use more power when you do this. Hopefully you don't do it for long, and then when you're done, you release it. Okay. My favorite topic, Bluetooth. I had an idea about a talk saying, is Bluetooth working yet? But we all know the answer. So. It's a sad story, especially on Android, and I'm not going to go into the details of the API so much this time. I'm just going to go through what you need to think about when working with Bluetooth low energy on Android. We're going to skip the whole Bluetooth Classic because it's basically going away. This is the architecture for Bluetooth low energy, and the highlighted box there is for the two profiles that are relevant for most cases. It's called GATT and GAP. And GATT is for communicating between a central, that's your phone, and a peripheral, that's a device you connect to. The client-server thing doesn't exist in the Bluetooth low energy world. They say central and peripheral, where they mean client and server. Generic access profile, that's for discovering. You basically set it in to listen for advertisement, or you go sending advertisements yourself. Advertising, super simple protocol. The peripheral with a regular interval, advertising interval, which is configurable by the peripheral, send advertising data. Now, the advertising data is really, really small. In later versions, it gets a little bit bigger and you can add more data. But in the basic version, it's about 20 bytes. That's what. So what they did also, they add the possibility for the central, when it gets an advertisement it might be interested in, to send a scan response request. Basically, it sends out a ping saying, okay, I'm interested in what this device is. Can you tell me more? And it will send a scan response data. Both on Android and iOS, this is nothing you have to implement yourself. It's done automatically by the Bluetooth LE scanner. But it's good to know, so then you get double the size of the whole 40 bytes. GATT is the connection thing, and it's basically message-based protocol. You send a message and you can receive messages within a connection interval. This picture isn't entirely correct because you can have places where the master just sends a package and there is nothing received. And you can also have the places where the peripheral sends data back to you, a notification. So, but to illustrate it, there is a connection interval and that's how it happens there. GATT is built up in this logical way, or, well, it's called logical way, but yeah. The profile is just a naming, that's the device itself. The service is just a logical grouping of characteristics, and the characteristics are your communication endpoints. That's what you read and write to. So you read and write to one or more characteristics usually. The most common way that people have implemented this is that they have two characteristics. One, which they write data to, which is sent to the peripheral, and one which they subscribe for notifications from, which basically means the peripheral is sending data back. So they're two separate messaging endpoints. The vast majority of the devices we see and we work with on Android for like companion devices are built up like that. It's somewhat not intended use case for it, because what happens here is basically it's no streaming. You just fake streaming by writing multiple messages on top of each other. And it has some challenges there. So basically what they realized, the Bluetooth spec people, they realized that, okay, people are using Bluetooth in a way we didn't expect, as is always the case with Bluetooth. So they came up with other solutions. We're going to look at that. Now, how are you going to work with Bluetooth on Android? Let's look at some code. I used to say, well, you have to write it yourself because there are no good libraries. Cable is now good enough to use. So now my recommendation is use Cable. When they came out first, it still had some quirks that required you to patch the library or work through it. But now it has a really nice API. It works cross-platform, both iOS and Android. So I highly recommend using this one today. There is a library in alpha version from Google, Android X Bluetooth. It's not production ready. It will never be production ready, as far as I know, because it's been in same alpha version for more than a year now. Anyway, this is how you do scanning with Cable. Super simple. And the important part to take away here is the Android specifics when it comes to connecting. It's that you can set up a peripheral once you got an advertisement from Cable. The three things to think about is you want AutoConnect false. There is a lot of confusion what AutoConnect means. AutoConnect for Bluetooth Low Energy GATT communication on Android means that you tell the system, please do a low power scanning in the background and connect once you find the device. If you have it false, to say, please try to connect immediately. And it will use more high power connection, shorter term thing. So it won't do scanning in the background as much. My recommendation is to not use AutoConnect true because it's going to connect slower. Instead, you do the scanning first so that you know that the device is there. And once you've found it, you connect, and then you don't need the AutoConnect set to true. The second thing is, in on services discovered, you do the request MTU. You don't do that later. You do it immediately. Actually, this should actually be done before on service discovered, but Cable doesn't allow you that, so you should do it here. In on service discovery, you request MTU size, and you don't request it more times during the connection interval, because according to the Bluetooth spec, you're not supposed to change it during a connection. The third thing is, if possible, think about using the PHY level, which is the physical layer level, where you control how much error correction you want on your Bluetooth connection. And by tweaking the amount of error correction you require, you can basically increase the throughput or increase the range. So by setting this to 2M, you get 2 megabit per second instead of 1 megabit per second. There is also one called coded, where you get, I think, 128 kilobit, and 128 kilobits, but you get a very much better range. So that's the trade-off you can do. The peripheral needs to support this. The peripheral can request this thing itself. It's basically a negotiation between the two devices. iOS does not have an API for this. I don't even know if they support 2M, but it's nice to know that you can do this on Android because you can actually improve the use case for your peripheral. How to read and write. It's also on the cable website, so I'm not going to cover that more. Now, the thing I do usually recommend when people start with Bluetooth Low Energy, if they start from scratch and they're going to build an embedded device that you're going to talk to over Bluetooth, I recommend to look at L2 cap. It basically exists in a lower level of this protocol layer. So you say, and what you can do here is basically you can get a connection-oriented communication over Bluetooth instead of this message-based GATT. It's actually much simpler to use. So you basically, this is a code, a very simple code, hello world thing. You call on the Bluetooth device, you call create L2 cap channel, and you pass it a protocol service multiplexer. That's an internal name inside the Bluetooth standard. It's a number that the peripheral will hand you in some way. How it gets to your device, to the phone, is a different question. But once you have that number, you can set up an L2 cap channel. And this L2 cap channel basically works like a socket. So you got an input stream and an output stream. And now you can do communication much easier. You don't need to go over the whole writing messages to GATT and all those things and all the deficiencies that comes with the Android API for that. This PSM, usually, that is something that you expose through a regular GATT characteristic. So you just basically connect with GATT first, read that one, and then you're done, and then you can connect with the L2 cap. That's usually how we do it. If possible, you can also hard code it in a QR code, and you got it there, or an NFC tag or whatever. How it's transferred is out of the scope for how the L2 cap is set up. So I recommend looking at L2 cap before using GATT today for new devices, if possible. New Bluetooth features. There are new stuff coming. LA audio, not so much for developers, but the cool thing here is that they have a new codec, which will make Bluetooth headsets sound much better. They got Auracast, which basically is multi-speaker in synchronized, and they got a standard called isochronous adaptation layer. Isochronous, well, something to do with time and the same, so you get it. And also spatial audio support. The interesting thing, especially for developer, is that in Bluetooth 6, you will have channel sounding, which is a really weird name because it doesn't have anything with sound, and it's not, well, it's a channel, but what it does is give you precise ranging and location. So between two Bluetooth devices that support Bluetooth 6, you will be able to accurately define the range and position between those two. So that's coming, I don't know, 5 years, usually, something like that. I know the Bluetooth 6 spec is still in progress or just published, so we'll probably have to wait before we can use it. One thing I'm going to talk very briefly about is an alternative to Bluetooth, because Bluetooth has like a theoretical range of 100 meters, sort of, in best case, usually much shorter. But if you have much higher requirement on range, there is something called LoRa. It's not supported by any phones, so you basically need a bridge, a router to bridge to that network. But basically it's designed for this use case. You have very long range, like 1,000 meters, maybe even more. They've done tests with a LoRa of like 13, 15 kilometers between two devices. So it can go pretty far. Really low bandwidth. So this is something you use for sensors that you're going to put out in the nature or something like that. So you need to design something like this, basically have gateways that convert it to IP traffic, and then you talk to those. So if you come into a project and you're going to have sensors and stuff distributed and you're going to work with that, how do you connect to them? LoRa is probably the answer you were looking for. Comparing LoRa with Wi-Fi BLE and cellular, it looks like this. Bandwidth is much lower, the range is much better, the power consumption is super low. Okay. Anyone heard of Matter before, right? A few of you. So you know this is the kind of thing that's going to fix all the problems with smart home. Yeah, people are not even laughing, I get. We've heard that before. So this is not a network protocol, it's more like an application level protocol, but I want to include it because we're going to talk about the next thing as well. So Matter is like combined together with Thread as a solution to all smart home stuff that we will see in the future. You've probably seen already that like the Google Home Hub is Matter compatible. The IKEA hub they have for their smart stuff can do Matter as well, etc., etc. I think the Apple has their thing as well, so they're all Matter compatible. And the way it works in the data structure is basically you have a Matter node. It can be a smart bulb, it can be a light switch, it can be something else. That one has a number of endpoints of a certain device type. Each endpoint has a number of clusters, and each cluster has attributes that can be read or write or both, and commands, which you perform an action on them. So, for instance, a light switch. You can have two. We have a light switch which has dimmable light also. So it's an on-off button and a dimmer. That will look something like this. You have a cluster that is an on-off cluster, and you have a cluster that is a level control, and then you also have another endpoint which is just the on-off, because a regular light switch might understand it differently. Sorry, this is a light itself. This is not a switch. This is a light, but it's what it presents to the world. So this is a smart light. The way it works then is basically you can have a dimmer switch which talks to both of those clusters, or you can have just a toggle switch which just talks to the on-off. And the way you work with this one is basically you provision your Matter device into your Matter network, you give it access to another device, and it's all encrypted, and it's all taken care of depending on which SDK you're using. So Google has their own SDK for this. Now, what kind of devices are supported? So if you go into the GitHub repo for this, you can scroll through the list of supported clusters. So these are the things that they have defined. These are the type of devices that are that exist in their world, like this and nothing more. So it's basically the same problem that Bluetooth did, where they tried to define device types for everything. This is why I think that Matter will be just a repetition of DLNA, if you remember that one, or Bluetooth itself. They're going to run into the same problem. And not just this, if you then go to check what does Google Home support, these are the clusters that one supports. So it doesn't even support all the clusters that is defined by the standard. And the same thing goes for other like bridges or Matter devices that's supposed to be the controlling everything. So if we come up with a new type of device that doesn't fit in here, well, sorry, you can't connect it to Matter, which is probably going to happen, right? Because we can't predict the future. Another problem with Matter is this, certifying devices. You have to go to them, pay them money, get it certified before it starts working with everything else. Yeah, so it's built for success. There is an API for Android in Google Play Services. You can find the API down there, how it works. It's fairly simple. Basically, what the API does is let you commission and provision Matter devices into your Google Home network. So it's an intent-based API for commissioning, and there's you can do some task communication with it as well. Fairly simple to use. It kind of works. I didn't run into any big problems. So I'm not even going to go through code examples here. They have a code lab that you can look at. I recommend looking at the primer to go into details about this, so you'll learn more. Now, the other thing with this one, I'd already mentioned that is Thread. That's an actual network protocol. That's a new one. It's starting coming out now. So if you buy the Google Home Hub, it has Thread support. If you go to, but I think IKEA has some Thread support in their stuff as well. But it's basically something that patches the gap between Bluetooth and Wi-Fi. It's low power. It's IPv6 compatible, so it uses IPv6 for everything. And it's defined to be able to have devices come and go as well in the network. Because, for instance, If you have a light switch, which is thread compatible, connects using thread, it doesn't have to be online all the time. It just has to be online when you push the button. So the whole protocol is designed to have devices that go down to sleep and disappear and then come back. I'm going to talk about how the network works, because that's the interesting part, so you understand that one. There is an API. I'm not going to show any code about that. You're probably never going to use that in Android. This is how a network works. There are routers and there are end devices. And an end device is only connected to one router. So a child only has one parent. Routers are connected to each other and their children. There is one thread leader. The thread leader is the one who controls and gives IDs to the other routers. Now, if a child disappears and a router doesn't have any more children, it can usually convert itself to become just a child to another router, because it doesn't have to be a router anymore. There's no point. There's nothing for it to route to. So they can do this dynamically. These devices, they figure it out. Then you also need a border router, which is basically converts this into the internet. That's what your Google Home hub does. It acts as a border router. Communication in this network happens on IPv6. And it's divided into 3 different networks. You have the global network, which is basically like outside the scope here. You have the link layer protocol, which is from the point of the central router there. When it only requires a single radio transmission, that's called a link local network. Applications will never use this. It's used internally just to address the next node. And then the more interesting one is the mesh local network, because this is where applications exist. So how does the IP addressing work? Because this is really, really smart, so I wanted to talk about this one. There is something in the standard called RLOC16, and each router starts with having a number. That's one you see there. That's what the thread leader does. It gives the number to these. It gives the ID to each router. And then all children has another number assigned from their router. Okay? And from that, those 2 numbers, you get an RLOC16. That is part of the IP address. We're going to see in a moment how that looks like. Now, if one router disappears, all this is recalculated. There might be a new number assigned to a router, so all the IP address changes again. So in the mesh network, everything can change, get a new IP address. So the RLOC16 is calculated in the following way. You have the ID for the router and the ID for the child. So in the case of the router itself, it doesn't have a child ID, so that will be 0. But in the case where the child has 1 and its router has 1, the RLOC is 401 hexadecimal, I guess. And that means you take the mesh local prefix, which is a predefined part of the IPv6, and you have the interface ID prefix, which is the second part there, and the RLOC16, and then you have an IPv6 address for your device. This all is calculated automatically, so there is no DHCP involved, and all that just goes away. The challenges with that part. So this is how Thread works. You can work with Thread on Android through the border router. So if you're not doing Matter and you want to provision something into a Thread network, there is an API for that. You can go there and look at it. Now, there's also a primer which goes into this even more in details, especially when it comes to how things are provisioning and how things are communicating externally and stuff, which I also recommend you to read if you're interested in diving into this one. Okay, ultra-wideband. This is, in my opinion, the coolest technology we have available on Android today. Anyone here tried using ultra-wideband on their phone? Yeah. Because it doesn't work well, and it's very few phones supporting it. But it's a really cool technology. So ultra-wideband looks like this on the frequency and power. So it's below the FCC limit for how much power you're allowed to do before you have to use the dedicated channel space. That's why it can be so wide, from 3.1 gigahertz to 10.6 gigahertz. So when an ultra-wideband device sends a message, it sends it across this entire spectrum. So that's why it's called ultra-wideband. But it's also very low power. But thanks to sending it across such a wide band, you get a much better delivery reliability, so to say. So, what's the use case? This is the main use case. Unlocking your car. That's basically like, or unlocking any smart lock. You're already probably using it today if you have like a recent car where you have your fob and you move close to the car and it unlocks. Or you move away from the car and it locks again. That's ultra-wideband, or an earlier version of that standard. It's called a ranging session, and it's very accurate because it can do the ranging and location in real time, and it can also detect if you're moving towards it or away from it, and from which direction. So if you have this on a smart lock on a door, it means it can detect if you're indoors moving towards the door or away from the door versus outdoors moving towards the door or away from the door. Which means you can build a use case where you lock the door when the person is leaving the home instead of just walking away from the door indoors. That is not possible with Bluetooth today. Maybe with Bluetooth 6 it will be, but we'll see. So, I mean, there are other stuff involved here as well, in use cases you can probably imagine. Apple uses this for Find My Devices, for some of them. Also, I assume this is what they use when you take your iPad and you place it on the left side, and your computer figures out that the screen is on the left side. That would be the likely use case for this as well. So we probably will see this used more, since it's so low power and it's very nice to put into any kind of device. The API. The API looks like this, or used like this. You get the system service with the ultra-wideband manager. You need to get the address. And here comes another challenge with it. In order to get the address and the keys that you're going to use for communication here, you need to have an out-of-band communication, which is usually done over Bluetooth. You connect with Bluetooth, you get that information, and now you can set up the secure ultra-wideband communication here. So the session key in this case is the case. Wondering why it's glitching. There, stay. It's once you have the session up, you get a flow with ranging information or ranging result that you can then use to just like subscribe to that one and get the accurate, like whenever it changes and gets that one, you can tell how far away it is. You can even tell which angle from your phone it is, if that is supported and if that is supported by both devices. Okay. I have almost 5 minutes left. So, questions? Yes, there. Oh, yeah. Yeah. You go first. So the question was if ultra-wideband requires line of sight. No, it doesn't. LoRa. Yeah, LoRa doesn't require line of sight, but none of these require line of sight, but it's better if you do. So the test they did with LoRa where they got like 13 kilometers or whatever it was, I think that was that's obviously line of sight. If you don't have line of sight, expect something maybe top 1,000 meters. But it's still, better than Bluetooth without line of sight, or Wi-Fi for that matter. So, yeah. Yes, that's. Yeah, for each session, you need the keys for there. So usually, like if you take the car example, the keys are hard-coded because there is no other communication happening there. So you could do it like that. You hard-code the keys and you're done. Or you transfer the keys over Bluetooth once because you go scanning for the device, you get a response, and then it's. You could have the device you want to locate could advertise the key on over BLE, and you don't need to connect to it. So there are many ways to do this. Indoor positioning works really great. When I've tested it, I get like a couple of centimeter accuracy, so it's really good. Yes?
Another question about the UWB. If the signal is distorted by the wall or the glass, does the material affect the strength of the signal distortion?
So the question was, is the material it passes through affected? Yes, but the fact that you have an ultra-wideband, so like material, like your wall will absorb different frequencies. So there is always one frequency that will go through. And since the same information is passed on such a wide band, it basically doesn't matter. But the power is not very good. So of course, like a thick concrete wall, it will never pass through that regardless of like what you do. So I don't know if that answers your question, but you don't have to worry about it. But the range of ultra-wideband isn't great. Think 10 meters. No, it does not. So FCC has a limit. This is a noise. There's a noise floor, and then there's a limit for like how powerful stuff can transmit. So since it's so, everything else that it interferes with, in this case just Wi-Fi on 5 gigahertz, also 6 gigahertz, it will just assume that is noise. So that's a good thing. Okay. More questions? No, good question. Yes? For ultra-wideband, this one here. Yeah, it's divided up in channels. I don't remember how big the channels are. I would assume they're very small, like Bluetooth, like a megahertz or something like that. Yes. So yeah, yes. Yeah, 5G. I was thinking about putting 5G into the talk as well. There are stuff you can do in Android to detect if you are on a low latency 5G network, which can be very interesting for many use cases. If you want to like have the real-time communication or controlling stuff in real time over 5G, like you don't have a Wi-Fi, you can't do Bluetooth or whatever. But yeah, it's very simple. It's basically you just go in and check the telephony manager what kind of network you're on, and then you can do that. So there's not much to talk about there, but that's the whole unique selling point with 5G is that it has low latency. Sure, it has a better bandwidth, but I mean 4G is usually good enough anyway. So the low latency is the unique selling point with 5G, and very good range, like across the world. Yeah, that's true. That's true. Yeah, I don't have a solution to that. Yes. The Pixel series since Pixel 7, at least the Pro ones. I think it's the Pixel 7 Pro, and then I don't remember exactly which one, if the regular Pixel 7. iPhone has support for a while. The Samsung, like expensive devices supports it. I think, yeah, so this is something that's a little bit troubling because it's not widely adopted on Android yet. I'm assuming it's because the hardware cost is too much. So as the price goes down, it's probably going to increase. Yes? You mean on Bluetooth? Yeah. Yes.
Doing lots of sending and receiving to lots of different devices. I was interested to see what there's an underlying system.
So the other question is, is there a mesh technology in Bluetooth that allows you to transfer information in the background? Not per se. It's a peer-to-peer protocol. But a central, that is your phone, can connect to multiple peripherals at the same time, and that's usually how it works. Now, you could do you mentioned it yourself, the broadcasting. That's sending advertisements. And sending advertisement is something you can do in the background. You just need to like implement the right services and the service type and everything that does that, and then show the notification in Android. That's the requirement. But then you can have your device broadcasting information, like using the gap profile in BLE. If you want to build a mesh network where you actually send messages, then you need to use GATT for that. That's usually what you do. Then you connect to GATT, you send the message there, and you receive messages, and when you're out of range, you disconnect it again. So no, there is no underlying technology in Bluetooth that does this. They do talk about like Bluetooth mesh a little bit and how to build it, but it's basically built up using GATT and GAP. Yeah. Okay, we're running out of time, but thank you very much for listening, and you'll find the slides online soon.